Hello everyone, I'm Hilay Shah, and today I will be talking about our work on investigating the strength of magnetic fields in elliptical galaxies. The majority of investigation done till date has been performed for spiral galaxies, mainly because they are large in numbers, easier to observe, and have substantial magnetic field strengths of a few tens of microgauss. On the image on the left, I show a spiral galaxy in optical wavelengths. It is evident that the spiral arms extend outwards from the galaxy in an orderly fashion. In the image on the right, the lines represent the strength and the direction of magnetic field lines. It is clear that these lines are aligned with the spiral arms that extend outwards, hence, they are known as ordered magnetic field. The ordered magnetic fields are generated because of the large-scale dynamics persistent in a galaxy. However, due to the turbulence present inside the medium of a spiral galaxy, there is a presence of small-scale magnetic fields which are not resolved in this image because of the inefficiency of the current telescopes to observe through. The magnetic field generation mechanisms are largely explained by the dynamo theory. In this image, I show a bicycle dynamo where the spinning wheel generates the kinetic energy that is converted into the electromagnetic energy by the virtue of this device. Similar processes are at work in galaxies where moving fluid particles generate sufficient kinetic energy that is converted into magnetic fields. The dynamo creates, amplifies, and shapes the magnetic fields of a galaxy, and the large-scale dynamics, such as well-defined rotation in the case of spiral galaxies, create fields that are ordered over large scales. However, due to the presence of turbulence, there are fluid particles moving at smaller scales, which also strongly amplify the small-scale magnetic fields. These small-scale magnetic fields have never been directly observationally probed yet. In this image, the differences between a spiral galaxy and an elliptical galaxy are shown. It is clear that the large-scale dynamics such as the well-defined rotation which shaped the arms of a spiral galaxy are absent in an elliptical galaxy. Additionally, type 1a supernova explosions create a turbulent environment. Thus, the turbulent small-scale dynamo amplifies the magnetic fields present in an elliptical galaxy, and observationally probing the magnetic fields of an elliptical galaxy would mean that we are probing the action of a small-scale dynamo. Before I show my results, I would like to explain a few physical concepts. When an electromagnetic wave travels through a magnetoionic medium, its polarization angle rotates. For instance, in this image, the initial electromagnetic wave is vertically polarized, and after passing through the magnetoionic medium, its angle of polarization has rotated clockwise. The quantity Faraday rotation measure is dependent upon the gas density of the medium, the ordered magnetic fields, and the path length through which the electromagnetic wave travels. Additionally, if multiple magnetoionic mediums are present in the path of an electromagnetic beam, then Rm fluctuations are present in that medium. These Rm fluctuations cause not only the rotation of the polarization angle, but also causes depolarization of the electromagnetic beam. In a radio galaxy, there are usually two lobes, one that points towards the observer and other points away from the observer. The first one is known as the jet and the second one is known as the counterjet. It's clear that the radiation from the counterjet has to travel more through the medium of the elliptical to reach the observer as compared to the radiation from the jet. Thus, if Rm fluctuations are present inside the medium of ellipticals, the radiation from the counterjet would depolarize more. In this image, the radiolobes are shown at two different wavelengths, and the lines represent the strength and the direction of the polarization. When the wavelength changes, the polarization angle rotates. But for the counterjet, which is the bottom part, there is also a depolarization. Thus, if we compare the polarization values between the jet and the counterjet, we can infer the strength of the small scale magnetic fields present inside the medium of the elliptical galaxy. We calculate the small-scale magnetic fields in elliptical galaxies using the described Laing-Garrington analysis. We adopt two different electron density profiles. The uniform profile assumes a constant electron density for simplicity, and the King profile has a varying electron density with the distance from the center. Thus, small-scale magnetic fields at the center of an elliptical can be calculated using the King profile. We obtain substantial magnetic field strengths in ellipticals of less than 3 microgauss. However, these are much smaller than the small-scale magnetic fields in spiral galaxies, which are about 15 microgauss. Additionally, we use the difference in the Rm values between the jet and the counterjet to calculate the large-scale magnetic fields in the elliptical galaxies. The strength of large-scale magnetic fields is extremely low. This is expected because there is a lack of large-scale dynamics in elliptical galaxies. We also calculate the small to large-scale magnetic field ratios, and it can be clearly seen that in the case of ellipticals, these ratios are much larger than the spirals. Thus, the small-scale magnetic field generation mechanisms are probably much stronger in ellipticals as compared to spirals because of the lack of large-scale dynamo and the prevalence of a small-scale dynamo. We use another method, that is by exploiting the polarization properties of the polarized emission from a background radio source to calculate the magnetic fields in the intervening galaxies. Suppose two observers are at two different locations and they observe the same radio source, with the radiation passing through elliptical galaxy for one observer and through spiral galaxy for the second observer. Then both of the observers would report different polarization properties for the same radio source. These differences arise because of the differences between the gas density, the strength of magnetic fields, and the path length of the intervening galaxies. In this map, the circles show the location of the background polarized sources, and the solid dots represent the locations of the intervening galaxies. We have classified the intervening galaxies by their morphologies. The orange dots represent the spiral galaxies, and the green dots represent the elliptical galaxies. Thus, by isolating the radio sources whose radiation passes only through spirals or only through ellipticals, we can compare the properties between those two galaxies and infer something about the magnetic fields in elliptical galaxies. Before we use the morphological classification between spiral and elliptical galaxies, we explore some general properties of the rotation measure distribution from the background polarized sources. It is expected that as the number of intervening galaxies increase due to an increase in the rotation measure fluctuations, the standard deviation of the rotation measure distribution from the background polarized sources would also increase. Thus, we assume a power law dependence of sigma Rm on the number of intervening galaxies. We calculate the power coefficient for three different number of intervening galaxies, where each intervening galaxy is assumed to impart a random rotation measure between the numbers mentioned in the brackets. Using this simulated data, we predict that when the number of intervening galaxies are low, the power coefficient is almost 1, and thus the power law assumes the form of a nearly linear dependence. Then we create a probability distribution function of the rotation measure from all the background polarized sources and fit three different functions, one Gaussian and two non-Gaussian functions to it. Then we calculate the standard deviation for the rotation measure data and for all these three different fitting functions. Now for a general data of all the intervening galaxies, we explore the dependence of the standard deviation of rotation measures on the number of intervening galaxies. By assuming a linear dependence, we observe that the slope in all the cases with the fitting functions and the real data is positive, but the errors in the slope values are very large to infer anything about the large-scale magnetic fields of the intervening galaxies. However, we do observe that the standard deviation of non-Gaussian functions are higher because of their ability to fit the outliers well because of tailedness. As we could not infer anything about the large-scale magnetic fields from the rotation measure analysis, we now exploit the polarization values from the background polarized sources by using the morphological classification between elliptical and spiral galaxies. We observe that the radiation of background polarized sources that only pass through the spiral galaxies have, on average, a lower polarization value. Hence, spiral galaxies depolarize more. This is expected because of their larger thermal electron density and stronger small-scale magnetic fields. Now, by assuming a small-scale magnetic field profile of a spiral galaxy, we compare the values of polarization between these two and calculate the small-scale magnetic fields in elliptical galaxies. We obtain the central small-scale magnetic field in an elliptical galaxy to be of around 6 microgauss magnitude. Thus, the small-scale magnetic fields in elliptical galaxies obtained using two different observational methods give nearly similar results with the magnitude of magnetic field strengths lesser than 10 microgauss. This is the most accurate and robust analysis done till date because it uses the latest datasets. These techniques described in this presentation could be useful with upcoming surveys like SKA, which will provide plenty of data for the radio sources with less error values. Additionally, the values that we obtain for the magnetic fields can be used to constrain the galaxy evolution simulations. We will be extending this work to analyze the magnetic fields in dwarf galaxies, and the paper that is accepted in MNRS for this work can be found at this link. Thank you.